Mass and inertia, mass and inertia. Some of these concepts are really sort of marginally 4A concepts, but we're going to go ahead and talk about them just a little bit. We said Newton's first law, and as I told you repeatedly, I don't care if you ever remember which is number 1, 2, and 3, is often called law of inertia. A force that is not being acted upon by an unbalanced force stays doing what it's doing, stays in motion, stays in rest. But let's think about the effect of mass on inertia. So, lead brick and a ping pong ball, you hit them each with an equal force. One of them has a larger acceleration. You know which one. Why? Ping pong ball, lead brick. Which one has the larger acceleration? Ping pong ball. We could test this out. I have ping pong balls. I don't have lead bricks, but I can find something. It's less massive. It takes a smaller force to get it to accelerate. Okay, well that's easy. You knew that. So we said that first law is inertia, and inertia is just proportional to mass. So the greater your mass, the greater your inertia. The harder it is to get something to move or get it to change its motion. When I was just out of college, I worked for the Division of Wildlife. I squeezed fish for eggs and sperm for a summer. I talk a lot about it in biology because it's quite relevant there. It was delightful, and my friends had lots of fun making jokes about my occupation. But as part of that job, they put me in the big truck with the big trailer and said, go. Okay. And I had never pulled a large trailer prior to that. I had driven large vehicles, but I had never pulled a large trailer. And what I didn't realize was how much that you're laughing because you've driven a large trailer. And I've had students in physics who chuckle because they go, yeah, been there, done that. Your stopping distance has changed a bit, isn't it? You've got a lot more mass. Therefore, it is harder to change the velocity of that vehicle because you have added mass to it. You need to allow more time for braking. It's going to take you more time to accelerate. If you've gotten stuck behind a truck on an uphill, it takes them more effort, it takes more force to change velocity. We know this. Now, what's interesting is that you can use that tendency towards inertia in braking systems. And your seat belt, have you noticed that when the car brakes suddenly, your seat belt locks? There is an inertial brake in there. So when there is forward motion, that brake kicks in. Same thing happens in trailer brakes. A lot of trailer brakes, you'll see, who's actually looked at a trailer hitch? Who's had to hitch up trailers? Okay. Have you seen the ones that have the little thing inside? That's an inertial brake. When the vehicle in front changes its velocity, it exerts a backwards force on that inertial brake, and that kicks in the trailer brakes. It's pretty ingenious. I don't have another good example of inertial braking systems, but I'm sure that there are some out there. So it's one of those things that just as you're moving through the world now, think about it. Oh, that's an inertial brake. Oh, cool. There are actually inertial braking systems on elevators. That is the one other place that I know of. Why is it a good idea to have an inertial braking system on an elevator? So it does not fall to the bottom of the shaft. So you have a system where when there is a sudden acceleration, when there's a sudden attempt to overcome inertia, the brakes kick in. Basically, the elevator starts to go too fast, it's going to brake. It's not going to drop to the bottom of the shaft. That's a good thing. We've been doing this. I sort of shortcutted introducing this, and apparently the person who writes my notes can't spell. Yeah, just ignore that. We talked a little bit about this, but we've only talked about it in terms of standing still. We're now going to start to talk about it in terms of motion. If something is not accelerating, if it's either moving with constant velocity or it's not moving at all, it's at rest, we say it's at equilibrium. And when it's at equilibrium, the sum of forces, the net force is equal to 0. You've been doing this. We keep saying, well, is it rising into the air or crashing down? No. Then what's the sum of forces? 0. Is it moving left or right? No. Sum of forces is 0. We're now going to move into problems where there is motion, but the sum of forces is still 0. Is that possible? Yeah. Constant velocity. You're still at equilibrium. And you've already been doing this. I used to not introduce that sum of forces idea until this point, and I find that it just works better to do that sum of forces from the beginning and get in the habit. Really, there's no problem involving forces for which a sum of forces setup doesn't help, because it allows you to very clearly, very immediately see what's acting on which axis. When you resolve those forces, if it's at equilibrium, sum of forces is going to be 0 on both axes, because all the total sum of forces is 0. So it's at equilibrium. We consider it to be at equilibrium. And again, that can be moving, or this is where we start to talk about things that are moving. So this is the second and third laws, and as I said, I don't care if you know which is number 2, which is number 3, which is number 1. I care that you can use them. But the second law is basically F equals ma. An object's acceleration is directly proportional to net external force and inversely proportional to mass. If it's heavier, it's going to accelerate more slowly given the same force as a lighter object. Ping pong ball, lead brick. So up till now, we've been saying that sum of forces on the x equals, and it's, force to the right minus force to the left. Okay. Or sum of force, and, up till now, oops, that's generally been 0. We haven't been dealing with moving objects yet. Or we've been saying sum of forces on the y equals all the forces up minus all the forces down. And generally, again, we've been dealing with things that aren't moving. It's 0. Well, now what we're saying is that the net force on an object is equal to its mass times its acceleration. The sum of forces on an object equals ma. As long as we're on one axis, this is not terribly difficult, because we can look at something that is, for instance, in some position on the y-axis, and we can say, well, its sum of forces is all the forces up minus all the forces down. Its sum of forces on the y-axis is also equal to its mass times its acceleration. And you can probably see where this is going. That means we can set those things equal to one another. So we can start to look at objects that are moving, and we can start to figure out either what forces are acting on them or how they're accelerating. We can even figure out their mass. And it's important to remember that this does not negate this, it works with it. That's the most common mistake in these problems. This is 4B. This is where we start on the practice problems for 4B, so grab a book. Okay, Roberto and Laura are studying across from one another at a wide table. Laura slides a 2.2 kilogram book towards Roberto. If the net external force acting on the book is 2.6 newtons to the right, what is the book's acceleration? Okay, well, we can take the really easy route here. The net force on the book, the sum of all forces on the book, is equal to 2.6 newtons to the right. The mass of the book is equal to 2.2 kilograms. We would like to know the acceleration of the book. And we can say sum of forces, or we can say net force. Well, we know that net force equals ma. Solving for that, net force divided by mass equals A. Gosh, this couldn't be any easier. 3-part algebra. Yay! Let me just ask you to do a little bit of dimensional analysis, because we can. Do you remember what newtons really are? 1 newton equals 1 kilogram meter per second squared. Divide that by kilograms. What do you get? Meters per second squared. Hey, we're looking for acceleration. Isn't that convenient? Astoundingly so. Yes. Okay, so it becomes 1.2 meters per second squared. That's really, really stinking easy. 1.2 meters per second squared is the acceleration of the book. Assigned are all the 4B book problems. And up to number 3, they're actually that easy. So, go. Okay. So the one little thing I want to talk with you about in like 2 minutes that we have is the situation where we have somebody. So if she's just hanging on this trapeze, if she's just sitting there, she's not moving left to right, so we know that she's at equilibrium on the x-axis, not total equilibrium. Sum of forces x equals 0, we're going to disregard it completely. If she's just sitting there, sum of forces on the y is also equal to 0, equals all the forces up minus all the forces down. Gravity, force tension. What if she's moving upward? What if she's being accelerated upward? Oh, that's what 4B gets you. That's where we go with 4B. So if she is being accelerated upward, one part of this is still true. This is still true. This is no longer true. So now, we got to get rid of that. We find that sum of forces on the y-axis does equal force up, force down, and we can make that a little bit more technical by saying, sum of forces on the y equals force of tension minus force of gravity, but it's not equal to 0. If she is being accelerated upward, what we also know that is that the net force on her is equal to what? Mass acceleration. Well, if her net force is equal to mass acceleration, I'm going to move her over a little bit. This is where we start to do this trick. This equals that. So force of tension minus force of gravity equals her mass times her acceleration. You cannot disregard gravity. In order to accelerate her upwards on that trapeze, just to hold her there, you have to overcome gravity. So you have to at least have something equal to the force of gravity in those cables as a force of tension. Now, if you want to actually accelerate her upward, you have to put more force on it. So, if we wanted to solve this for force of tension, if we're given her mass, we're given her acceleration. Let's say we are. So, mass of the person in the trapeze, 75 kilograms, accelerating upwards at 1.5 meters per second squared. Do we have enough information here to solve this? Yeah, we do. So if we want to solve for force of tension equals mass acceleration plus the force of gravity. The force of tension in those cables has to actually be greater than the force of gravity, or she's just sitting there. And I can give you a real-world example of this where physics can save your butt. All right. We know that Fg is actually equal to mg. If we had to, and there are circumstances where we will do that, you can factor out mass. That's a handy trick to know. But in this case, what's the force of tension on that cable? Well, force of tension equals, it's actually easier to factor out the mass, but I'm not going to do it right now, times 1.5 meters per second squared plus, I'm going to have to move this all over, 75 kilograms times 9.81 meters per second squared. We got a raw number? Okay, so for raw numbers, I'm showing 848 and pocket change newtons. A good question to ask might be, how much additional force does that acceleration put on the cable? How would you find that? Could you find that? Of course you could. All you have to do is compare this number to the whole thing. It puts a significant, just that little tiny bit of acceleration puts a significant additional force on the cables. You'll have some problems that look at that very issue. So years ago, my husband dropped a key, a very important key, down into something. And it needed to be retrieved. Now, we have a collection of rare earth magnets at home. Don't ask why, we just do. Out of old computer hard drives and all kinds of weird stuff, and they live in different places. But we still weren't sure. The object was magnetic, and it was, we did have a magnet, and we could get the magnet down in, but the concern was that the magnet wouldn't hold it, because it was a fairly heavy object, wouldn't hold it all the way up. And I said, no, I got this. What's the trick using this? You know this trick subconsciously. Somewhere in your life you have used this trick, but you didn't understand the math behind it. You keep, what is it? The question is, how do you do it? How do you do it successfully? How do you maximize your chances of success with that magnet and that heavy metal object and not dropping the thing off the magnet? What's the trick? Huh? No, you can't use any more magnets. Slow. You minimize acceleration, because the bigger this is, the more additional force you're putting on that cable or that magnet or whatever. You've known that trick your whole life, but you didn't know the math behind it. Now you do. Isn't that nice? Isn't it nice to apply math to things you already know? You go real slow. Spoiler alert, I got the darn key out. Ha! He said it couldn't be done. So anyway, okay, that's it.